Hi student, welcome back to chemistry class with Emerald, and in this class today we are going to be looking at intermolecular forces. This video is brought to you by Igota Virtual Learning, and of course we are going to be looking at definition of intermolecular forces, the difference between intermolecular forces and intramolecular forces, and the others. Okay, so let's look at intermolecular forces. Intermolecular forces are the forces of attraction and repulsion between molecules. They are the forces of attraction and repulsion between molecules. Of course, we must be able to differentiate between the intermolecular forces and the intramolecular forces. Intramolecular forces, on the other hand, are electrostatic forces that holds the atoms of a molecule together. They are electrostatic forces that holds the atoms of a molecule together. So example of these intramolecular forces are covalent and ionic bonds. But for intermolecular forces, we are looking at the van der Waals forces, which is generally the names that they are called. And then these van der Waals forces are usually into different types as well, where we have the London dispersion force, the dipole moment, and so on and so forth. So intermolecular forces are typically weaker than the intramolecular forces, and account for generally the bulk properties of matter, especially the melting and boiling points. The intermolecular forces are responsible for melting and boiling points of matter generally. So let's look at a key difference again between the intra and intermolecular. For intramolecular forces, they are chemical bonds. They are the forces within a single molecule. While for intermolecular force, they are forces between individual molecule. They are forces between individual molecules. Now, a typical example is for intra. Now, for intramolecular force, which is strong, this is that within molecule. Like, look at the intra. We are saying they are forces within a molecule. Like when you have HCl molecule, this is a typical bond, a typical covalent bond or even ionic bond that could exist between chlorine and hydrogen. When chlorine can gain electron from hydrogen, so that it can become 288, while hydrogen can lose electron, so that it becomes 0. So they still attain stable test structure, and then of course they will form an ionic bond, H plus Cl minus. Now, of course, they can also share electron from the 287, from the 7 valence electron. There is one electron can be dropped for sharing, while hydrogen also drop one electron for sharing, so that it can form a single covalent bond as well. So this is the bond that is formed here is intra, because it's between that molecule. But for intermolecular force, it is it's a force that is formed uh, within a single between individual molecules. The force within individual, so that means the force that is formed within chlorine and the one that is formed within hydrogen, that is intermolecular force. So of course we know that intramolecular force, like we have said, is stronger than that of intermolecular force. Now note that like we have said, in the inter, like covalent bond is strong, that of inter it is weak. The intermolecular force, however, are strong enough to control physical properties such as melting and boiling point, vapor pressures, and viscosity of uh, elements and compounds respectively. So let's look at it again. In intermolecular forces, there are forces of attraction or repulsion that has between neighboring atoms. And note that they are responsible for physical and chemical properties of matter. Why, uh, of course, we must also note that uh, the intermolecular bonds are caused by attractive force between negative end of a molecule and a positive end of the other. Intermolecular force is attractive force between molecules. Therefore, the higher the polarity, the higher the intermolecular force between the molecules. Now, let's look at what polarity means. Um, polar, in terms of polarity, now we could have polar substances and non-polar substances. An example here is when we say polar, that means it has two poles, the positive and the negative, where you have partial charges that are here. HCl, H2O, NH3. These are polar compounds because they have positive and negative. But in terms of non-polar, for instance, nitrogen, CO, and then CCl4. They are non-polar because they do not have uh, positive and negative pole. So what is the major difference between them? For non-polar molecules, they are not soluble in water, but they are soluble in non-polar solvents. But polar molecules are soluble in water. Um, Non-polar molecules are volatile. Polar molecules have low volatility, they do not easily evaporate. Non-polar molecules have low melting and boiling point. Polar molecules have relatively high melting and boiling point. Non-polar molecules are not very dense. Polar molecules are very dense, and so on and so forth. So these are some of the key differences between polar and non-polar molecules. So generally, when we are classifying intermolecular forces now, or van der Waals forces as the case may be, we can now classify them as non-polar, uh, non-polar, polar, and polar, polar. Now, for non-polar, polar, you could have the London dispersion force. For non-polar, polar, you could have dipole-induced dipole. Then for polar, polar, you could have dipole, and hydrogen bond. Now, let's quickly look at some of these things that we were talking about. So, for intermolecular forces, we could have dispersion. We also call it London dispersion force. London dispersion force is present in all molecules and atoms, and this is the molecular perspective of it, where you have partial positive and negative charges that are created within those molecules. Then its strength is between 0.5 to 40 kilojoules per mole. Then when you have a dipole moments or dipole attraction, usually occur in polar molecules alone. And then you observe that it has also positive and negative poles, but its own strength is greater than the strength of London dispersion force. Then again, we have hydrogen bond or hydrogen bonding. Hydrogen bonding occurs with um, uh, hydrogen atoms containing compounds. That means uh, compounds that are containing hydrogen, most especially highly electronegative elements that are bonded to hydrogen, e.g. HF, H2O, NH3, etc. You will also observe that electrons are moving from the positive to the negative in this case, and of course the strength is higher than that of dipole. And then you have ion dipole, which is a mixture of ionic compounds and polar compounds, and then which has the greatest strength here. Okay, let's quickly look at the dipole force. For the dipole forces, they occur between molecules that each have a permanent dipole moment. That means they occur in polar molecules, simply put. And we have looked at what polar molecule is and their properties. So each of the ends of the dipoles possess um, uh, delta, a Greek letter that is called delta. They possess partial charges, and in these partial charges you have the positive pole, which is delta plus, which attracts the negative pole, which is delta minus of another. This is an example of a dipole-dipole force, where you have hydrogen chloride from the negative aspect or the negative um, part of the HCl, which is on the Cl, is interacting with the positive aspect of another HCl, which is on the hydrogen. So a dipole-dipole moment is created in that order. Then the same thing with water. The positive, the negative O is combining with the positive H of another. So that's how dipole moment is created. Okay, so you could and some of the properties of dipole-dipole attraction now is that it only occurs between two permanent polar molecules, and then the positive end attracts the of one attracts the negative end of another, and then the bond strength is between 5 to 20 kilojoules per mole, and then the dipole-dipole attractions are weaker than ionic and covalent bonds. And of course, in terms of application now, is find its application in determining the properties of a substance. That's number one. They are also significant for formation of stable compounds, including biological organisms. Then soft adhesives uses dipole-dipole force that allows them to stick on to the surfaces. So because of that, some of the applications of dipole-dipole interaction therefore will be in medical industry, in construction materials, in electronic devices, and in sports equipment. Okay, so let's look at the charge-induced dipole forces. The dipole-induced dipoles and ion-induced dipoles are example of charge-induced dipoles. The dipole-induced dipoles and ion-induced dipoles are an example of charge-induced dipoles. Dipole-induced dipoles occur between a polar molecule and a non-polar molecule, while ions-induced dipoles occur between an ion and a non-polar molecules. Electrons here can be pictured as cloud, and then the polar molecule or ion distorts that electron cloud of a non-polar molecule by pulling it away towards a positive charge or pushing it away from a negative charge, creating a temporary induced dipole moment. So this is an example of a dipole-induced dipole forces. You can see it an example in HCl, for instance, where you have um, polar and an induced dipole that is present on argon. So when HCl and argon interact, for instance, the negative end of Cl will now interact with the positive end of argon. Don't forget that the argon here have what is called an induced dipole, positive and negative charge. So this is how dipole-induced dipole are created. An example is when also water, which is a polar substance, interact with oxygen. In oxygen as well, there is an induced dipole. So the negative end of the water molecule, which is on that oxygen, we add with the positive end of the oxygen molecule, which is on the first oxygen. So this is how a dipole-induced dipole forces are created. Okay, so let's look at a few of the questions here. You have to consider the following type of bonds: the CN and CH, CN and CO, and CF and CO. We want to look at which bond in each pair is more polar, and then we should arrange them in terms of order of increasing order of polarity. Now, if you are able to do that, you observe that in Cn and Ch, Cn is much more polar. Cn is much more polar because temporary dipoles are created around this. Then in terms of Cn and Co, Co is much more polar, and then in terms of Cf and Co, Cf is much more polar. If you observe clearly, you will notice that between H and N, N is more negative than that of OH. So there will be a temporary induced dipole that will be created on N. So that is why it's more polar. Then the same thing, O is much more electronegative than that of Cn. Then F is also than N rather, and F is more electronegative than O. So in terms of increasing now, Cf is greater, and then Ch is the lowest there. Then again, we can look at chemistry 2019, which of the substances is non-polar here? And the answer is bromine. Why is bromine? Ammonia is NH3, and N is joined together but with 3 hydrogen atoms, and then all the hydrogen atoms are positive. So ammonia is polar. Water is having 2 hydrogen atoms, and the hydrogen atoms are polar there, and then hydrogen atoms are positive rather. In ammonia, hydrogen atoms are positive, then there is negative on the nitrogen. So you have positive pole and negative pole. So ammonia is polar. For water, you have positive pole of the hydrogen, negative pole on the oxygen. So water is also polar. And then for hydrogen bromide, you have positive on the hydrogen, negative on the bromine. Hydrogen bromide is also polar. Only bromine, as bromine molecules you have, which is Br2, we have negative. That's why it is non-polar. Now another one is this question: the molecule that has a non-polar covalent bond. A non-polar covalent bond. So predominantly, the 4 of them present here could have they have a covalent bonding in them. However, the only one that is non-polar is Cl2. HCl is polar because you have H plus Cl minus NH3, H plus N minus there, H2O, H plus O minus. So the 3 others are polar. Only Cl2, which is Cl minus, is a non-polar covalent bond there. And then again, we can look at another question. We have to state the type of intermolecular forces present in hydrogen fluoride and argon. Hydrogen fluoride will have a hydrogen bond. Why? Because hydrogen bond is formed between hydrogen and highly electronegative element. An example is fluorine. So hydrogen bond is formed between it. So the intermolecular forces in hydrogen fluoride is hydrogen bonding. Now for argon, it is van der Waals. Van der Waals force is an electrostatic force of attraction or repulsion between molecules. And examples of substances that has van der Waals force are noble gases. All noble gases have van der Waals, the alkane family, the halogens, the CO2, etc. So these are the answers respectively. So far so good. We have looked at what intermolecular forces are, the difference between intermolecular and intramolecular forces, and then how intermolecular forces link with polarity, and then the types of we now say we have polar substances and non-polar substances. We look at their examples and differences. So we also able to look at uh, some of the few questions under this topic reviewed. So you can take more questions on intermolecular forces and study them respectively. Continue to learn chemistry. See you in the next video, and bye bye.